Hello, my name is Prachit and welcome to my channel. So in this video I'm going to do bit banging and I'm going to store data in this EEPROM IC 24LC256 and also I'm going to read data from the memory location. So first I will store, then I will read. So I'm doing this all by manually controlling the bits by this push button. That means I'm going to implement I2C protocol using push buttons. I've used a red LED for the clock indication and green for the data. I'm not the first one who's doing this. It's actually done by a YouTuber called Kevin Darrah 11 years ago. I'm inspired by his video. He beautifully explained how to random write and random read in this IC. But further, I researched and I figured out how to sequential read and sequential write. Sequential writing is very easy. He also said in his video that you can do it, but sequential read is very tricky because first you have to issue the acknowledgement, then again you have to send the 8 clock pulses, and again you have to send a stop, then again start. Okay, and I will show you how to do that. So let's make this circuit, and now let's get started. Let's do bit banging. So we'll power on this. So right now SDL and SCL both are high. So now let's write data to it. So first we will initiate the start by pulling the SDA line low. Then we will send 1, 0, 1, 0. So on rising edge of the clock, the data is stored. So 1010 is the control code which is fixed that we have written. Now we have to write 3 zeros, which is the address A2, A1, A0. Okay, so 0, 0, 0. Then the last bit, so we are writing, right? We are not reading. So again we will store 0, 0. Now we should get the acknowledgement. I will release the data line and you can see that it's being pulled low, and I will clock in the acknowledgement. It gives us the control back. Now I will write the high address byte 0, 1, 2, 3, 4, 5, 6, 7, 8. So you can see we have got the acknowledgement. We have written the high address byte. We'll clock in the acknowledgement. Again I will write the low address byte 1, 2, 3, 4, 5, 6, 7, 8. So I've written 8 zeros in the low address byte. I've got the acknowledgement. Okay, and when I will give a rising edge of the clock, this 0 will be clocked in. Okay, so on the falling edge it will give us the control back, and now we'll write the data byte. So what was our first data byte? 1011. So I'll give a rising edge here 1, 0, 1, 1, 0, 0, 1, 0. So yes, we have written the data byte on the address location 0, and now we've got the acknowledgement. We'll clock in the acknowledgement, and now the address location is incremented. Now it's 1. So I will write the next data byte on the address location. So I will hold the line low 0, 0, 0, 1, 0, 1, 0, 0, 1. So I got the acknowledgement. Okay, I will clock in the acknowledgement, and now I will write the data byte 2. So first I'll write a 0, 0, 1, 0, 0, 1, 1, 1, then again a 0. I got the acknowledgement. Okay, and now I'll clock in the acknowledgement. It gives us the control back. And now see how to generate the stop signal. So to generate a stop signal, first you have to shift in a 0. So you have to pull down the address line and you have to release the clock, which will give a rising edge and store a 0. So when the clock line is high, you have to give a low to high pulse on the data line. So right now the data line is low. I will release the data line and this will stop. The start command is giving a falling edge when the clock line is high, and the stop signal is giving a rising edge when the clock line is high. So right now we give a stop command and now this data is written in the address locations. So this is how we write the data in this IC. So the data is permanently stored in the address location, and now to get the data back, we need to initiate the read commands. So we'll turn off the power and again turn it on to show that the data is non-volatile and we are getting the same data back, and it's an EEPROM IC. So we initiate the start command, then we give the write control byte. That's because we are writing the address. Even though we are reading the data, okay, we are writing the address. That's why I give the write control byte. After start we give the write control byte, that is the same byte with the last bit 0. Okay, so we give this command, then we give the high address byte, then low address byte. Then after this, as we are not writing the data, we are reading it, we'll again start, and at this time now we will give the read control byte. That means the same byte but with the last bit 1. So after giving the read control byte, we'll generate 8 clocks, okay, and these 8 clocks on the each falling edge of the clock will get our data back from the SDA line. It means each individual bit will get back. So after the 8th clock, there's no acknowledgement from this SDA line. So we have to know that we have to generate a stop command after the 8th clock. That means once we get our data back, you have to generate a stop command. And after giving the stop, to read the next data byte, we have to again give the start command, then the read control byte, then the 8 clocks, and again the stop command. Then we have to repeat the sequence. This start, read control byte, 8 clocks, then stop, okay, to read each consecutive byte up to. So now let's give commands to read the data from the memory location. So first we give the start command, then we give the write control byte. So that's 1, 0, 1, 0, 0, 0, 0, and the last bit is 0 because we are writing. We got the acknowledgement. Now I have to write the high address byte, which is all 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So we got the acknowledgement. Clock in the acknowledgement. Now I have to write the low address byte. 1, 2, 3, 4, 5, 6, 7, 8. So we got the acknowledgement, clock in the acknowledgement, we got the control back. Now instead of writing the data byte, we have to read. So I have to take this route to again send the start command. So I will make the clock line high and I will pull the data line low. So this is a start command. Now I will send the read control byte, which is the same byte with the last bit 1. So I'll send 1, 0, 1, 0, 0, 0, 0. The last bit is 1. So I got the acknowledgement, okay, and clock in the acknowledgement. But now on the next falling edge, I will get the first bit of my data, which is data byte 0. So it was 1, 0, 1, 1, 0, 0, 1, 0. Okay, so this data I got from the output, and now on the next clock both lines become high, and again I have to send the stop command. Okay, so this was the stop command, then again the start command, and I have to again send the read control byte. So that is 1, 0, 1, 0, 0, 0, 0, and the last bit is 1. So now I will get the data byte 1, okay, 0, 0, 1, 0, then again it is 1, 0, 0, and the last bit is 1, okay. So now again I have to send a stop command. So that I will send by, first I have to pull the clock line low, then the data line low, clock in a 0, then pull the data line again high, so that gives a low to high pulse when the clock line is high. It's a stop command. And again we have to generate a start command and then send the read control byte, okay, 1, 0, 1, 0, 0, 0, 0, the last bit is 1. So now I'm going to get this data byte 2. So the first bit is 0, next bit is 1, then again 0. So just take a look that on the falling edge we get our data, okay. So on the next falling edge we get a 0, next falling edge 1, next falling edge again 1, next falling edge 1, and this is the last bit, so we get 0. So on the next falling edge put will again become 1, okay. So we don't get any acknowledgement here, so we have to generate a stop command once we receive all the 8 bits. So now we will generate the stop command, okay. And in this way we got our 3 bytes that was returned to 3 address locations. Now let's send this sequence with the help of a microcontroller. So instead of push buttons, I will send this commands with a microcontroller, and I have written a code for it. This is the code that I have written in KLID to automate the bit banging process. So from here I can set the write control byte, the read control byte, the high address byte, the low address byte, the data which is to be sent to the EEPROM chip. So everything can be managed from the program. All you need to do is press these 2 push buttons. One is to read, so the memory contents will be read and put it on the output port 1, and one button is to write. So when I press this button, this data, okay, will be returned to the memory location 0. So for now it's doing only random read and random write. So now I will press the button which will read the memory location 0 and put it on the port. And you can see this data which was previously written by bit banging. So here the LED which is on means 0. So it's 1011 0010. So the same data, right? 1011 0010, which is written on data byte 0 location. So I'm going to change the data byte here. So I will make it 1 0 1 0 1 0 1 0. So let's upload this code. Okay. First I will save it, build it, generate the hex file. So in case you are new to Nuvoton microcontroller, you can watch my tutorial on Beginner's Guide to Nuvoton microcontroller. Okay. So this button is to read and this is to write. So first I will write the data. I will press this button and write the data to the memory location. So the delay is 1 millisecond, so it will happen very quickly. You see? In the blink of an eye, the data was written. Now you press this button, it will be read and it will present on this port. So yes, this was the data 1010 1010. So these LEDs are connected in common anode. So the ones which are lit that means it's 0. So data is 1010. It is the same data that we have entered here, 1010 1010. So in this way we can interface a EEPROM I2C chip to a microcontroller, okay, to a 8-bit microcontroller, and in this way we can interface other I2C modules also if you understand the data sheets. Okay, so yes, this was the video in which I showed you how I2C works. I hope you found this video useful. Like this video, subscribe to my channel. Thanks for watching.